All right, let's get started. Today we're going to work on this thing called kernel support vector machine, or we are going to go over the support vector machine as well. But since this is the kernel series, we're going to talk about kernels. So this is the Northeastern University course, and I am Professor Wu. Okay, so SVM. Today we're going to learn this, and then we're going to kernelize it. It's one of the most famous early classification algorithms. The idea is pretty easy to understand as long as you remember some of the math. Okay, and the prediction is pretty accurate. So, this idea of support vector machine, also known as SVM, was initially invented by Vapnik. Vapnik. It has a very beautiful theoretical background, and there are multiple versions of this, like the linear version, soft margin, and the kernel. So you're going to learn these here. Okay. So let's very quickly review linear projection. The idea of projection, if you have two vectors, v1, v2, is if you're projecting v1 onto v2, then you're essentially drawing a perpendicular line along, and you want to essentially be able to find the distance from zero to the point of intersection. So you want to be able to find the distance, and you would like to find this point D. Okay, so this is a distance, and you would like to find a point. So if you're able to do both of these, then essentially you're doing projection. That was from projecting V1 onto V2, right? If you have V2 onto V1, right, then the vector will look something like this. So the perpendicular will look slightly different. Okay? So that's depending on who is projecting onto who, the idea is slightly different. Okay. Before we do that, now remember I'm pretty sure we've done this in the previous videos, where the concept of a unit vector is a vector where the length is 1. So this right here is length 5. So this is not a unit vector. This right here is length 1, as you can see, 1. So this is a unit vector. This is also length 1. So when you have a vector that is not a unit vector, so this is length 5. So this right here is 3, 4, right? So if this is not a length 1, all you have to do is divide by the length. Okay, so 1 divided by 5, and now you will get length 1. Okay? All right, so when you do linear projection, right, if you're trying to find this distance here between 0 to D, right, you're trying to find this distance. All you have to do is take, let's call this U and we'll call this V. All you have to do first is to find the unit vector of unit vector. So U is a vector here, but what you do is you find the unit vector. And this distance here, from here to here, is simply v dot u hat u hat. So u hat is the one being projected onto. Okay, v is doing the projection. Therefore, the one that's being projected onto is the one that has to be normalized. And there are geometric reasons why this calculates the distance automatically. But we're not going to get into it right now. All you need to know is if you want to find this distance d, you simply have to do the dot product between v and u hat. Okay, v and u hat. And that will calculate the distance. And if you see that this right here, u hat is approximately this, right? Because this is 4, 2, and that's the vector. And if you divide by the distance, which is 1 over square root of 20, this is u hat. Now, the other vector is v here, which is 2 and 3. So if we dot u hat and v together, right, then it'd be 2 and 3 times 4, 2, giving us roughly 3.13. And you can see that this makes a lot of sense when we zoom in. So if this is approximately 3, this being slightly longer than 3.13 makes a lot of sense. So this distance, like you see, can be calculated simply by taking the dot product of the two vectors. Now, once you know the distance, right? If you know u hat, and you know the distance, remember u hat is length 1. So if you know length 1, if you want to find the point D, it's simply the distance times u hat. Distance times u hat. And that gives us the point D. Okay, so that's how you simultaneously find the distance as well as this exact point of intersection. Okay, so um, do a quick practice, see if you can essentially solve these problems. Right, you have two vectors, right? You want to find this point D. Okay, see if you can do it. Once you get a little bit warm up, like these concepts, even though you may have done it before, like just priming your brain first will help you to understand it later. Okay. Now that you have done that exercise, we can start looking at the simplest form of support vector machine. Let's assume we have two classes. Support vector machine is essentially an algorithm that does classification. It distinguishes between different classes. So when you're doing the classification, you have different classes, and we'll start with the simplest when we only have two classes: a set of points that we'll call them blue, and a set of points we'll call them red. Okay, these are the simplest binary classification. Okay, and how can we tell them apart? Well, we can tell them apart by drawing a line and say on one side of the line is blue and on the other side is red, right? So if we can find a line that divides the two classes, that's the way SVM does it. Okay. So what would be a simple rule that will allow us to do this? Like I said, drawing a line. So here is the equation of a line, right? X1, you see X1, X2. Well, that's one way to draw a line. Another way, it looks like this, right? You plug X in, you got Y out. So you can draw a line both ways, this way or this way. But for the sake of, they're mathematically equivalent. For the sake of this problem, we're going to stick with this one. Okay, so this is the way we're going to draw a line. Okay, so on the right, you can see the example of a line that essentially separates the blue and the red. Okay. Now over here, the reason why we like to write this way is because we're not necessarily only going to deal with two dimensions. We may have more than two. So here's two, then sometimes we may have three, we may have four. So writing it this way allows us to represent all the W's as a vector and all the X values as one single X vector as well. And then this can be converted into the vector W times X plus B. Okay, so they're equivalent. They get right equivalent. Now this form is better because it doesn't matter what dimension you are dealing with, you will still essentially use this form. Okay? So if we have this equation, which is equal to 0, means that if you plug an xy value, it has to be along this line, right? That's how we describe this line. So therefore, this equality equal to 0 has to satisfy. You plug whatever x value along this line, right? The result is that it will give us a 0, right? It will give us a 0. But what happens if you give us a positive value and not 0? Well, if you give us a positive value instead, like if you plug an x in, it gives us a positive value. It means it's above the line, right? It's higher than the line. If you give us a negative value, it means it's below the line. This implies that we can essentially identify on the one side and the other side by using what is above the line and what is below the line. Okay, so if it's above the line, then we can simply say that this point must be part of the blue. If it's below the line, then we can say that these points must be part of the red class. Okay, so the fact that we can simply look at if this is positive or negative, right, greater than or less than 0, positive or negative, it essentially allows us to identify if a point belongs to one class or the other. Therefore, if we can identify a line, an ideal line, if we can identify this line, then we simply can use the function sign, right? The sign, whatever you're putting inside the function sign, if this is positive, it's going to return 1. And if it's negative, it's going to is return 0, right? So if it's greater than 0, means positive. 1. If it's less than 0, then it's going to be um, a negative 1. Okay, so this right here is how we can do classification once you identify the ideal W. Okay. Now, one observation here we need to make is that line scaling doesn't change anything. What does that mean, line scaling? Well, let's say we have a line, right? What will happen if you multiply 2 on both sides? You multiply 2, you multiply 2. All right. So 2 times 0 is still 2, and 2 is here. So if you multiply by 2, is this a different line? The answer is not. I mean, you can try to draw it out yourself, but when you multiply by 2, in fact, when you multiply by any number, 10, 100, 1000, you're still getting the same line. Okay? So line scaling, the magnitude of this doesn't matter, right? It's still the same line. In fact, if you were to multiply by any constant, because it's the same line, whatever is greater than this line will still be greater than the same line, right? By multiplying this alpha value to the line, you are making this line, you're stretching this line, but it's still the same line, right? It's still the same line. So this implies that if you have the line, the W value, the magnitude of this whole thing doesn't really matter, right? This is the equation. The magnitude doesn't matter. You can multiply by anything you want, and it will still be the same line, right? So this is will change the stretch the line, but it won't change the whatever's above and below, and therefore the classification won't change. So that's the second thing you need to realize about lines. Okay, so now that we've like primed you to understand this, then the idea is, how do we then go about finding the best line? Well, there are infinite ways to draw a line. Like if you draw a line like here and say everything above is blue, everything below is red, this is obviously a bad line because, well, they're not all red, like, and you have nothing here as blue, right? You can also draw this line and say everything above is blue, everything below. So this would be a bad choice, right? This one will also be a bad choice, and this would be a relatively good choice. So how do you know? How do you know what is a good and what is a bad choice when you have essentially infinite ways to draw lines, right? How do we mathematically then model the concept of a good choice? Okay, so to do this, we need to have two logics. Okay, logic number one. Logic number one. Note that in binary classification, previously you may have done logistic regression, which is 0 and 1, right? So in this particular case for SVM, we're going to set it up so it's not 0 and 1, it's negative 1 and 1. Okay, so negative 1 for red and 1 for blue. Okay, so that's logic number one. It's just how we label things, and we can label to anything we want. And therefore, here for this particular case, we're going to pick negative 1 and 1. Okay, logic number two. Remember, if it's blue, it means it's above, so we're going to get a positive value. And if it's red, it's below, meaning we're going to get a red. Okay, so those two facts, if we combine them together, is what will allow us to come to some like realizations. So if we combine logic 1 and 2, for blue points, if you multiply the label by this, well, blue points, if it's positive, then it's going to be positive, right? Because it's 1. And if it's blue point, it means this is going to be greater. Remember, greater than 0. Therefore, if you multiply them together, positive times positive is always going to give you a positive value. So if you multiply them together, the and this is positive, right? This is a label, and if you got the W such that this is also positive, then you got a positive value, implying that you did a good job. Okay, so over here for red, remember red is a negative. So if you take the label, multiply by the line equation, well, the line equation should give you a negative value, right? It should give you a negative value. Therefore, negative times negative is a positive value. This implies that if you pick the correct W value, if you did, if you pick the correct one for blue points, this should be positive. However, if you pick the wrong one, right, then this is going to be a minus, resulting in a minus. So if you did a correct one, the multiplication of this will give you a positive value for blue points. The multiplication for red points should also give you positive value. Therefore, if this, whatever this is, you make it as positive as possible for every single sample, then this essentially will measure the correctness. Okay. Remember, imagine if you picked a wrong W. If it's a wrong W, then it's going to pick negative instead of positive for the blue point, and that's going to result in negative, right? So if it's positive, it's correct. If it's negative, then it's wrong. Similarly here, if you picked a, a, a wrong W, so instead of negative, this would have given you a positive. A positive times negative will give you a negative again. So notice you get the wrong, if you pick the wrong W, you're going to result in a negative value. If you pick the correct W, then you're going to result in a positive value. So if you put all the samples, add up all the samples, you find a W that gives you as much positive as possible. That means you get as much correct answer as possible, right? From this logic, regardless of its red or blue points, if this is positive, it means we got the correct classification. So we conclude that this is a condition. If this is positive, greater than 0, it means that we did a good classifier. Like if for all the points you put in, if all of them are positive, then like it means you picked a good W. Okay, so if we pick the good W, if we sum up all the possible points, right, it means if and we maximize, so we find a W that maximize this relationship, then we will essentially find a W that makes everything positive, hence correctly categorizing each sample. Okay. Well, so you might think this is enough, right? Because at the end of the day, that's what we want. We want a W that correctly classifies the samples. However, that's actually not good enough. Imagine if we did pick a W that can properly classify. So every single sample here will give you positive. However, notice all these lines are good lines. Every one of these lines will give you essentially the best, a perfect classification, right? If I draw this line here, everything above blue, everything below red, check. I can draw another line here. Everything above is blue, everything below is red, check. So you can imagine, even if you can do a perfect classification line, you still have infinite lines to choose from. So which line among them then will we say is the best, right? Then how do we judge if every one of them already give us perfect classification? Which line has to be the perfect one? Well, let's take a look. We can see that this line, not this line, um, this line here, right? Let's treat this. So let's call this line 1. Well, line 1 is obviously a line that gives us perfect classification. However, it doesn't give us a lot of margin for error, right? Because if we screwed it up, if the blue point is like right here, or red point happens to be right here, then you made a mistake, right? So this concept of margin for error seems to be able to help us and guide us to come up with a better line. Ideally, if we draw a different line like this, notice how now the margin for error is much bigger. So if it's slightly off for red, like here, slightly off for red, it is still okay because the line's right here. So this right here is called a margin. So if you're able to pick not just any line, you want to pick the line that simultaneously give you the correct prediction as well as the largest margin for error, then that's just one line, right? Instead of infinite line. And that is how we would determine and define what the best line is. Okay. So so okay. So right here, like I said, this is the perfect line. And this right here is the margin. So we want to maximize the margin. Also, we're going to call these points, the data points, that's basically right on edge, the closest to the other class as support vectors. Okay. So these are some vocabulary, margin, and support vectors. So the idea is we want to pick a W that maximizes the margin. So how do we mathematically represent the margin? Okay, so let's try to mathematically define the margin. But before we do that, one more thing you need to realize. Um, you need to first realize a very important insight. And that insight is that when you have an equation of a line, this one, right? This is the equation of a line. Well, this W is a vector. This W is a vector. And this vector is always, and I mean always, perpendicular to the line. So, so over here, notice this is the equation of a line, just like this. This implies that W is 2, 1, right, times X, right? So this is W transpose X. And now if we were to draw out this vector W, 2, 1, then it will look like this, W21. You see? And notice how W is perfectly perpendicular. Perfectly perpendicular. So if this is the case, then like this is something that's very helpful to realize. Okay. So ideally, I would like you to draw this out so that you can convince yourself, right? So right now, ideally, you pause this video and draw this line. Once you draw this line, and then check if W here is perpendicular. Once you check if W is perpendicular compared to this line, then you should be convinced that they're perpendicular with each other. And after that, pick a random point and draw the shortest line from D. So once you have this, pick any point. When you draw the shortest line to the line, this should be parallel to W. Okay, so these two should be always parallel with each other. So try to convince yourself of these two facts. Once you're ready, we'll move on. Okay? So remember, we're trying to mathematically define this distance, right? Which we call margin. Okay. So to do this, we are going to define this point as xp and this point, which is the support vector, the point that is closest to the other, right? The point that's closest to the other class, right? So therefore, you can see that xp plus this vector d, xp plus d is equal to x hat, right? xp plus this vector give us this, which implies that xp is equal to x hat minus d, right? Right here, x hat minus d. So now we have an expression for this point, xp. Now remember, this distance d is parallel to w, right? Yeah, so this right here is exactly the same, pointing in the exact same direction. Therefore, d is really just w multiplied by some constant, right? So if you take d, w, and multiply by some value, like and compress it, then it's gonna look just like d, right? So this vector d can be written in terms of w. After that, we know d, so let's plug d in inside the original equation, giving us a new representation of xp. So xp could be represented as x hat minus alpha w. Okay. Since the point xp is on the line, remember the point. This is a line, right? So this point is on the line. It implies that if we plug it into the line, so if we plug xp into the line equation, this has to be satisfied. It has to equal to 0. So this has to be true. If this is true, well, we knew what xp was, so we're going to plug xp in here. So after we plug xp, then we have this expression. We can start simplifying this expression by multiplying w to the both sides. Okay, so now we have x transpose and then this here. Now notice there's only we can assume to know all the variables. We know w, b, all these. So we can now solve for alpha. Okay, so after we solve for alpha, it results in this expression. So now remember, why do we want alpha? It's because we are trying to mathematically represent this margin, right? And this margin D is represented by alpha and W. So if we know W, well, by knowing alpha, it essentially tells us this vector D. Okay, so we now know D is equal to alpha times W, and we know alpha now, so we now have an expression for D. Okay? Well, once we know D, where alpha is equal to this, if we know this vector, how do we know the length of this vector? Well, it's the L2 norm. So by calculating the L2 norm here, the L2 norm, which is D transpose D, and then take the square root. So we know what D is, which is this expression. So we're going to plug that into D and D, and now we end up with this. So from here we plug it into DD, and then we know W. We're just now going to plug alpha in. So we plug alpha square. So here's alpha square. Notice how W got copied here and alpha square got copied here. Now, after this, this W here gets canceled out. So it's just one, right? So only one of them. This right here is a square, and when you take the square root of a square, then it becomes the absolute value, the magnitude of the line, divided by the norm. So you take the square root here, that becomes the L2 norm. So here's the expression of the margin, right? So we can mathematically say the margin is equivalent to this. Now, what were we trying to do? Well, we're trying to maximize the margin. That's what we wanted to do. So what we have now is we have two objectives. Objective one, we want to find the W that maximizes this expression. Remember, this expression, if it's positive, then it's a correct classification. So we want it to be as positive as possible when we add up all the samples. So this right here essentially measures the correctness. And this one is the mathematical representation for margin. So we want to simultaneously maximize the correctness as well as maximize the margin. Okay? So now we have the mathematical representation for both of them. Remember earlier, we said the goal is to find a classifier, right? When we're trying to find this classifier, we did not care the magnitude. We can make this as large or as small as possible. We only really care about the sign, right? Therefore, the magnitude doesn't matter. Magnitude doesn't matter. Well, if the magnitude doesn't matter, we can set the magnitude to any value, right? So we can set this to 1 just to make life easier. So if we can set this to 1, we can now just get rid of this and turn that into 1. And that makes the whole expression easier, right? Right? We take this, get rid of it. Now it's much easier to solve this because we don't care about the magnitude anymore. Okay. So now, once again, we have the objectives. So this leads us to the objective. We are trying to maximize the margin, right? And we want W to be as positive as possible. So we want all these to be positive. And we would like this value, remember the magnitude, to equal to 1. To equal to 1. So alternatively, we can rewrite this. Maximization is equivalent to minimization. When you're trying to minimize, it's equivalent to minimize the square. So adding a square here doesn't really change anything. So this right here is a problem. It's a constraint optimization problem. We want to maximize the margin such that it gives us the correct assessment that this turns out to be positive, and the magnitude is equal to 1. Now, if we look at the two constraints, this one and this one very carefully, it's saying that the support vector uh, has to be at this point with the length of 1, right? That's what that's saying. And over here, it's saying that 1 times this value has to be greater than 0. Well, we already know this point has to be greater is 1, right? So therefore this distance is at least 1. Therefore, it can't be just greater than 0. If we combine the two logic, then it's at least greater than 1, right? So all the points has to be here. That's what that's saying. And no points can be here because, right, it has the nearest one. So this is saying that the support vector right here, the support vector, right, it's saying that the support vector distance is at 1. So if the nearest one is at 1, therefore this has to be greater than 1, right? If this so we can combine both of these logic. Instead of this, we can get rid of it and simply say that this has to be greater than 1. Okay. And this makes life easier because now we only have one constraint. Right? Okay. Well, so we now have a problem where this has to be greater than 1, and we're trying to maximize the margin or minimize the inverse of the margin. All right. Okay. All right. So, so this is the objective, and notice we're not optimizing when we solve for W, right? When we solve for W, it turns out that B gets canceled out. So we can do B completely separately. B is not used during gradient descent, and we can easily find B later. So, okay, and how can we go about doing that? Well, if you want to find B, right? Remember that the goal is to create the classifier function, right? So we want see the sign, right? If this is positive, that means this is greater than 0, and if it's negative, it means it's less than 0. So notice after we take all the blue points, we project them. So these are the different blue points, right? Then the distance for all the blue points must be is approximately, this is to the first one is 4.1, the second one is 4.4, and the third one to here, that distance is 4.8. Right? So after we do the projection, we know all the distance to every single point. We know the distance to all the points after projection. We also know all the distance to all the points in red, right? So we know the points here and we know the points here, right? And therefore, notice how we know that if we know the distance to every one of this point, right? If we set B to the midpoint right here is the distance is minus 3.1. Okay. So if we put minus 3.1 into this equation, right, we put the middle, then notice how 4.1 minus 3.1, that's going to be a positive value, giving us 1. And then 4.4 will give us 1 because all of these subtract by 3.1 will give us a positive value. Okay. Conversely, notice all the red points. These are all the red points. When we subtract B, which is 3.1, the midpoint, it's going to be a negative value, hence returning a -1. So from this observation, you can see that the b value, right, is simply the inverse distance minus distance from here to here, right here, right? So that's equal to b, right? So once you know that, it's pretty easy to find b. So basically, with SVM, you would solve it, find the support vectors, and then you will calculate the midpoint. All right, so if you know the distance from here to the support vector, and you know the distance from here to the other support vector, we're going to call this distance um, distance A, and we're going to call this distance C. So the midpoint is simply the distance A plus distance C divided by 2. So that's the midpoint. And remember, we make it minus so that you can create a positive here and the negatives here. Okay, so that's how you find B. Now, okay, so that's how you find B. Now we want to convert the problem into a Lagrangian. So this right here is a constraint optimization. If you turn it into a Lagrangian for every single sample, then turns out that you have multiple inequality constraints. I should have used gamma here. Yeah. Pretend I use gamma. I lambda is for equality constraint, but whatever. I pretend I use gamma here. Now we can solve the Lagrangian. You can solve the Lagrangian using the KKT condition, right? But for this particular case, it's pretty simple. So for simpler cases, we could actually just end up using a gradient descent. So for this simple case, I'm just going to set all the lambda to 1. I mean, yeah, like since we've done KKT condition, you know that lambda equal to 1 may not be good enough. But this is a really simple case. I'm just going to set it to 1. Okay. Once I set it to 1, then we end up having this expression here, right? Notice we set the lambda to 1. So now, if we want to run the gradient descent, all we have to do is take the derivative. So this right here, what is the derivative of this? Well, it's 2w. And the derivative of this is equal to, with respect to w, it's equal to xi, yi, right? Now, 2w we can't simplify any further, so we copy 2w. But this part we can. Notice it's x1 times y1, x2 times y2, so we can rewrite it into this form. This is simply x transpose, the data transpose, and this is the y vector. And therefore, we now 2w minus x transpose times y. Now, if we set this to 0, then we basically have the solution. So this particular one, problem, give us like the closed form solution for w. Okay. Alternatively, like if you don't have to use the closed form solution, you could use gradient descent. Gradient descent. Where's gradient? Here's gradient descent, and you just use the derivative over and over again. Okay. So that's alternative way to solve this. Okay, so I wrote the code for you guys. So this is the particular easy case, and then I ran gradient descent using the derivative, and I can show you what it looks like at each step. Let's see, gradient descent right here. So this is the video. This is the video on running gradient descent at SVM. Now this line, green line here, is the W vector, right? So you can see that the W vector is constantly perpendicular to the actual line itself, and it's essentially, and the red dot is B, is the midpoint between the midpoint between the support vectors. Okay, so I mean, eventually it will converge. So that's the point. Okay, all right. Let's see.